Foxy. Okay, pause. All right, now the foster kitty is turning into a lap kitty that won't take no for an answer. All right, so that's pretty much it for just simple kinetic energy. Now let's start putting it together and doing some math. All right, so first thing we have is our system and our surroundings. Okay, we always have to, whenever you're reading a problem, starting a problem, you always need to kind of have a feel for what the system is that you're focusing on in the problem versus what the surroundings are. So let me explain. The system is the part of the universe that we are studying in an experiment. The surrounding is everything else in the rest of the universe. Everything besides your system is referred to as the surroundings. So in a reaction, the reactants and the products are your system. Okay, the container and everything else, even the water that the reactants and products are dissolved in, are the surroundings. Okay, it's only the stuff that's reacting that's your system. So water, if it's, a spectator or just the other part of the solution, is the surroundings. This matters, okay, so remember this. Now, sometimes we'll have a closed system, a system that can exchange energy with the surroundings but not matter. Okay, we'll even do some labs like this. So a closed system can allow energy, usually in the form of heat, to be gained and lost, okay, out of the closed system into the surroundings, but matter won't be exchanging with the surroundings. So thermochem is simply the study of a heat change in chemical reactions. So we need to identify our system, the specific part that we're interested in, and surroundings, which is everything else. So here we have three different kinds of systems. Okay, in our first situation, heat can go in and out of the bottle here. Heat can enter and leave our system, but water vapor, which is matter, can also enter and leave the system. So, and be exchanged with the surroundings. Everything outside of the container is the surroundings. So this is an open system. Why would we call it open? Because it can exchange matter with the surroundings. Water can evaporate and condense and enter and leave the system and enter and leave the surroundings. Okay, so in an open system, the mass and energy are both exchanged. Now this is a closed system. This is what we will do. And that is one in which heat can be exchanged with the environment, but the bottle is closed off, as you can see, so matter can't be exchanged with the surroundings. So if only energy can enter and leave, that's called a closed system. And then this isolated one, we'll do a calorimetry lab like this, where we don't allow matter to be exchanged with the surroundings or energy. It's an insulated container. Okay? So we'll try not to let energy be exchanged with the surroundings. There's no perfect way to do that, but if you do, it's called an isolated system where nothing exchanges places with the surroundings. Okay, so in our last unit, we saw this diagram a lot with the piston here. Okay, well, with this piston being located right here, matter cannot enter or exit the system. Okay, the piston and everything outside of that is the surroundings, and let's just going to apply that. Okay, now putting it together with work. Okay, transferring energy. We can do that with work and heat. So from physics, we know that the force is the push or pull on an object. We know that work is the energy used to move an object, and that's equal to force times distance. So lifting an object, you're working against the force of gravity. Heat then is symbolized with the letter Q. It's the energy transferred from a hotter object to a colder one between the system and surroundings. So as you probably already know, there is no such thing as cold. Okay? There's either heat or lack of heat, but there's no such thing as actual cold. Like cold can't move from one object to another. You can't make something cold. You can, however, pull the heat away from it. Okay? Heat is a real thing that can be measured. Cold is just the absence of heat. And heat always goes from the hotter object to the cooler object. And energy is simply the capacity to do work or transfer heat. So when we go to figure out the energy for a system, we have to consider both the work done, if any, and the amount of heat transferred. All right, so we looked at similar contraptions sort of in the gas unit. We've got a piston here, and here we have a little container off to the side that contains zinc, and then we have some hydrochloric acid down here. So when you rotate this, that allows the zinc to fall in with the hydrochloric acid, and you're going to generate hydrogen gas, and it causes the piston to move up. Well, in the last unit, we learned that, well, that means there's greater pressure for the hydrogen than there is for the atmosphere, right? But now we can take it a step further, and we can actually calculate the amount of work done by our gas. It moved the piston. It applied a force over a distance. So the gas did work. I know it's kind of hard to think of. It's not like it took out the trash or something, but it did do chemical work, or physical work, I guess. All right, so whenever a gas expands, it's doing work. Okay, so here's another example. Combustion of methane in a furnace, if you have a gas furnace at home. Okay, there's the chemical reaction for it. The system is the methane and the oxygen and the carbon dioxide and water being produced. The surroundings is the reaction container, the furnace, and the room, and, well, really the whole house. Okay? And heat's going to flow out of the system to the surroundings. Where does that energy come from? Well, a mole of CO2 and water, and the 2 moles of water, that actually has less potential energy stored in the bonds, so less chemical energy, than our reactants, than the methane and oxygen. So we started out with a bunch of energy stored in the bonds, and then we released a lot of it when we rearranged those atoms and formed new bonds in the products. So energy was released from the system to the surroundings. Okay, putting this all together into a math equation. 5.2 in the text has to do with the first law of thermodynamics. We know that one already. It states that the energy cannot be created or destroyed. The first law of thermodynamics is also called the law of conservation of energy. So that is, the energy of the system plus the energy of the surroundings is a constant number. Okay? It's just energy flows from the system to the surroundings and vice versa, but it stays constant. Okay, so energy transferred from a system must be transferred to the surroundings and vice versa. Okay, so the total energy of the universe is constant. If it seems like our system's losing energy, it must be being gained by the surroundings. So we need to remember that in our calculations that we'll do. So now, internal energy, yet another kind of energy to throw at you. The total energy of a system is called the internal energy. It's the sum of all the kinetic energy and all the potential energies of all the components of the system. Okay, we can stick a thermometer in something and get an idea of the kinetic energy of it, but that doesn't tell us the potential energy. So absolute internal energy cannot be measured. We can't directly, there's not an internal energiometer, okay, that we can use to directly measure the internal energy. But we can figure out the changes in internal energy, and that's represented with a delta E. Delta means change. Delta is just a Greek capital letter D. So delta means change. So a mixture of hydrogen and oxygen has a higher internal energy than water does. That's why the Hindenburg went boom. All right, the internal energy of a system is the sum of all those kinetic and potential energies, like I said, and all we can do is figure out the change in internal energy. So the change is just mathematically represented here as the final energy minus the initial energy. Now, that number can either be positive or negative. It just depends. If we start out with an initial energy up here and we end up with only this much energy, see this is increasing internal energy on the side there. If we start out with a lot of energy and then end up with less energy, the energy of the system decreases. Well, that means energy was lost to the surroundings, okay? And that's a bad thing. So we'll end up with a negative delta E. Now, if on the other hand, we start out with very little energy, and energy comes in from the surroundings, and so our system ends up with more energy, okay, that's a positive delta E. The system gained energy. Okay, here's another energy diagram. You need to just get used to looking at these. They're going to pop up quite a bit. So here's that Hindenburg reaction, okay, the hydrogen combusting and forming water. Going from hydrogen and oxygen to water results in a negative change in internal energy. It released heat. It lost heat to the surroundings. So the delta E is going to be less than 0. It'll be some negative number. Now, if the delta E is less than 0, that means the system released energy to the surroundings. And the other word for that, which you've probably heard before, is exothermic. Thermic means heat, exo means exit. Okay, so exothermic, exo means outside or exit. There's a couple different ways to word it. Exothermic simply means heat left, heat exited the system. It wasn't lost, though. It went somewhere else. It just went into the surroundings. All right, now going the other way. Okay, if you were to take water and turn it into hydrogen and oxygen gas, you can do that. Okay, it's called electrolysis. That results in a positive delta E. Okay, you actually have to supply energy to the reaction, run electricity through the water to get it to do this. Okay, so if the delta E is greater than 0, that means the system absorbed energy from the surroundings, and that's called endothermic. Heat entered is what that means. And the cool thing is these, whatever this number is, it's going to be exactly the same, just a difference in sign. Okay, so I forget how many kilojoules are released with this one. It's been a couple years, sorry. But whatever amount of heat was released when the water formed, that's how much heat is going to have to get put back in to turn it back into hydrogen and oxygen. So the delta E would be the same going both directions, just in one direction it'll be negative, in the other it will be positive. All right, now relating all this to work. Okay, we know from the first law of thermodynamics that when a system undergoes a physical or chemical change, the change in internal energy is given by the heat added to or released from the system plus the work done on or by the system. So here's our mathematical equation, not too bad. Delta E equals Q plus W. The change in internal energy is equal to the heat plus the work. So we just got to add two numbers, right? Well, we got to make sure we have the right signs for the Q and the W. Is it positive or negative? All right, so heat is just the transfer of energy between two objects. It's exothermic if heat exits the system. Okay, that's a negative Q. It lost heat. The system did. Endothermic means heat entered the system. It gained heat from the surroundings. So that would be a positive Q. Oops. Okay, so when ice, that's what that's supposed to be, is ice melting. Foxy, no. Sharpening her claws on the furniture, sorry. When ice melts, energy has to enter the solid water in order to turn it into liquid. All right, now work, that's force acting over a distance. This one gets a little weird, I think. When a gas expands, it's doing work. It's applying a force over a distance, okay? The work is being done by the gas. So energy is exiting the system. When the system does work, that's a negative W, okay? It's, just look at it like this. We're all lazy, right? We don't want to do work. It's a negative thing if somebody forces us to do work. Well, the system, the gas in this case, feels the same way. If the system does work, that's negative W. Okay, if the surroundings push on the gas and squeeze and compress the gas, then it's like getting a massage. It's a positive thing. Okay, if work's done to the gas, then energy enters the gas, and so that's positive W. All right, so if a system does work on the surroundings, if a gas expands, that's negative W. If a surroundings do work on the system, that's positive W. All right, I'm out of time.